You probably saw lots of problems like this in your pre-calculus or college algebra class. Here we're asked to graph a particular polynomial function, x cubed minus 3x. Since you didn't know about calculus, the best you could do was to factor this. I can see you can pull out an x, and then you have x squared minus 3. You can actually think about this as x squared minus the square root of 3 squared and say, hey, that's the difference of squares. So you have x times x minus root 3 times x plus root 3. Then you could see easily where the function was crossing the x-axis. Say, okay, when x equals 0, I know I'm on the x-axis, or if x is the square root of 3, I know I'm on the x-axis, or if x is the negative square root of 3. At that point, you probably turn to the highest degree term, knowing that x cubed likes to go up to the right and down to the left. You would know that the function likes to do this. Right? Since each of these zeros has multiplicity 1, you know that as you come up you'll have to cross through, and you'll go up a ways but eventually have to bend back down in order to cross through the x-axis again, or cross through the x-axis again, yeah, and then eventually you'd have to bend back up in order to create this picture. So you got to sketch that way. But the first time you saw that, it wouldn't surprise me if you had a question as to where exactly does it reach this local minimum, or where does it reach this local maximum? Now that we know about calculus, we can tell the answer, because since the derivative gives us the slope, we could just look for a highest point by finding places, or a lowest point by finding places where the slope is equal to 0. So knowing calculus, we can now answer that question you had back in pre-calculus. If we take the derivative, we get 3x squared minus 3. If we factor out the common 3, we have x squared minus 1. That's a difference of squares, since 1 squared is 1, and we get x minus 1 times x plus 1. Now we can see that that's supposed to be the derivative, that the derivative is 0 when x equals 1. That means that the slope must be 0 there, and when x equals negative 1. So we've located these two peaks by finding where the derivative was 0. Now we know that it achieves this local max when x is negative 1, and this local min when x is 1. Right, it's called a local max because there are places where the graph gets even higher. It's not the maximum, but it is the highest point around. So locally, or relative to the others, it's the highest point. So a local max or relative max. This is a local min or a relative min. You can actually even find out, actually even distinguish between local maxima and local minima by looking at the second derivative. If we go back to this function and take the second derivative, we get 6x there, right? Which tells us that before x gets to 0, the graph is concave down. So in particular, the second derivative at that level spot where x is negative 1 is negative 6. That means you know it's level and it's opening down. So you can tell that this must be a relative max because it's level and opening down. On the other hand, if you look at the second derivative at that other place where the slope was 0, then you get 6 times 1 is 6, right? Since this is positive, you know the slopes are increasing, that creates something that's concave up. So at this point 1, it's actually level, and at that point it's concave up, and therefore this must be a relative min. Of course, if the second derivative is 0 at one of those level spots, then you really can't tell which it is. You might try this. Look at the function f of x equals x to the 4th. The first derivative is 4x cubed, so there's a level spot at x cubed. The second derivative is 12x squared. So at that place 0, the second derivative is 0. I'm not sure if it's concave up or concave down. Of course, if you look at the graph of x to the 4th, you can tell it's like x squared, only flatter, so it's not quite a parabola, but it is sort of U-shaped. You can tell that it's a min looking at the graph, but you can't tell from the second derivative test. So when the second derivative turns out to be 0, that's when the test fails. If you compare that to this case with x to the 5th, the first derivative is 5x to the 4th, and the second derivative, you can see that the only place where the derivative is 0 then is when x is 0. Then the second derivative is 20x cubed, and if we plug in, so we know that it's level at x equals 0, And if we plug the 0 in here, we get that the second derivative is 0 as well. Because you think about the graph of x to the fifth, it looks like this and like this. It's just got a level spot in the middle. It's neither a max nor a min. But you can't tell. The second derivative was 0 in this case. It was also 0 in this case. You can't tell whether or not it's a max or a min if the second derivative isn't positive or negative. Let's look at an example where we could use this to optimize, to find the highest or lowest value. A lot of times we want to do the cheapest thing, or we want to build the best possible thing, and that involves some kind of optimization, and that involves looking for places where the first derivative is 0. So in this example, we're supposed to make a box that has an open top and a square base, and it needs to hold a particular volume, so 200 cubic centimeters. What dimensions will minimize the amount of material required to make the box? So of all boxes with that kind of shape that hold 200 cubic centimeters, what dimensions will minimize the amount of material required to make the box? Let's just draw a picture here so we can see what's going on. We've got a box. It doesn't have a top, so there's no top here. It's got a square base, so this length this way is the same as the length that way, and it's going to have a particular height. And the question is, how do we choose these dimensions so that our box with no top will hold 200 centimeters cubed and use the least amount of material? Now, if we look at this holding 200 centimeters cubed, that's about the volume, right? And the volume of this box would be x times h, or x squared h. That has to turn out to be 200. What we're interested in, minimizing it, optimizing, is the surface area. And you can see this box is made of 5 pieces, right? There's a base, and then there's 4 pieces all the way around here, so 5 pieces together. Now the size of the base is x squared, so that's the amount of material, in a sense, that you'll need, right? The area tells you how much material you'll need to make the base. Now each of these sides is x by h, and there are 4 of those, so 4x by h. This is the thing that we want to minimize. And this is a pattern that you'll notice. Quite frequently you need to maximize or minimize subject to some kind of constraint. So if your boss says, build me the fastest car possible, probably he won't say the sky is the limit. He'll say there's some constraint on your budget. Build me the fastest car you can for $100,000. Build me the fastest car you can for $1 million, and so on. There will usually be some kind of constraint in the problem. Okay, so when the thing that you want to optimize, the one you want to make as big as possible or as small as possible depending on the context, when that thing depends on more than one variable, for now, we'll have to do something to get it in terms of just a single variable. Usually that involves turning to the constraint. So right now our surface area is a function of x and h. I want to get it to be a function of h alone, but the constraint can help me. The constraint says that h has to be 200 over x squared, just solving the constraint for h. Now I can plug that in here, and I'll have the surface area as a function of x alone. I'll have x squared plus 4x, and h is 200 over x squared, sorry. So if I simplify, I have the surface area as a function of x as x squared. Let's see, 2 times 400 would be 800, and this x cancels one of those, so we have 800 over x. If you think about this function, here's that dimension x that we choose. As x gets larger and larger, 800 divided by larger and larger numbers, if they're really large, that will disappear. Eventually this goes to 0. And then what you're left with is just something that looks kind of like a parabola. So over on the far end we know it looks something like this. On the other hand, as x comes back down to 0, so you have a small value for x, a small number will go into 800 many, many times, so this is very large, whereas a small number squared is even smaller. So over here, the graph is climbing up. I'm not exactly sure what happens in here. This would depend on whether the graph is always decreasing to a point, or maybe there's a bunch of ripples, I don't know. But something like that, there's a chance to have a minimum somewhere in here. And we could find it by searching for a place where the slope is 0. So what we do is we look at the slope. That's the derivative. We take the derivative with respect to x. We've got x squared plus 800 times x to the negative 1. I'll write it that way so we can use the power rule. We get 2x, and that's the derivative of this first piece, and then we get minus 800 x to the negative 2. X to the negative 2, of course, means 1 over x squared, so there's your derivative. Looking for places where the derivative is equal to 0, we set that derivative equal to 0, and we get 2x equals 800 over x squared, or if we multiply by x squared, 2x cubed equals 800, so x cubed equals 400. So x, that would be the cube, x would be the cube root of 400. So there's only one place where the derivative is 0. So there is this location. Now, is that what we expect? Is it a min? Well, we could always check by taking the second derivative. If we take the second derivative, the derivative of 2x is 2. The derivative of minus 800x to the negative 2 is plus 1600x to the negative 3. So if we look at the second derivative at our location of interest where that derivative is 0, the cube root of 400, we get 2 plus 1600 over, this is 1 over x cubed, so 1 over the cube root of 400 cubed would be over 400. That's 2 plus 4, which is 6, that's greater than 0. So we know not only is it level there, it's concave up there, and so yes, this is a min. We should make x be the cube root of 400, and then we'll have our minimum value. Now, they asked for the dimensions. I've got one of the dimensions. I know x. This is going to have to be the cube root of 400 times the cube root of 400. What's the height got to be? Well, I can always get that from here, right? The height needs to be 200 over the cube root of 400 squared. Okay, so I just need to simplify that. Best thing I could do probably is to multiply top and bottom by the cube root of 400. My reason for doing that is now I'll have the cube root of 400 times itself 3 times. That'll just be a plain 400. So we'll have 200 times the cube root of 400 all over 400. Of course, 200 will go into 400 twice, so we have the height is 1/2 the cube root of 400. Okay, so we can see that the height should be half of the base in this case in order to build a box that holds this particular fixed volume with the least possible amount of material. We did it by finding the flat spot and then figuring out whether that was a max or min by looking at the second derivative.